Stephen William Hawking was an English theoretical physicist, cosmologist, and holder of the Lucasian Chair of Mathematics at the University of Cambridge. In the academic world, he was known for his contributions in gravitational singularity theorems in general relativity and the prediction that black holes emit radiation and hence have finite lifespans. Hawking was born on the 300th anniversary of Galileo's death on January 8, 1942, to Frank and Isabel Hawking. He was raised in a family that placed a very high regard on education. Eventually, the young Hawking would go on to read physics and chemistry at University College Oxford at the age of 17, 1 year ahead of his peers. Hawking estimated that he only studied about 1,000 hours during his 3 years at Oxford, which is averaged to less than an hour a day. Frustratingly, these unimpressive study habits made sitting his finals a big challenge. So he decided to answer only theoretical physics questions rather than those requiring factual recollection. Hawking desperately needed a first-class honours degree, as it was a condition of acceptance for his planned graduate study in cosmology at the University of Cambridge after leaving Oxford. His exam results was on the borderline between first and second-class honours, making a Viva, an oral interview, necessary. He was concerned that he was viewed as a lazy and difficult student, but in fact was held in much higher regard than he believed. His apparent intellect was obvious to many, including his tutor, who said, "During the Viva, the examiners were intelligent enough to realize they were talking to someone far cleverer than most of themselves." In the end, Hawking successfully received a first-class degree in physics and began his PhD work at Trinity Hall, Cambridge. Sadly, it was about this time that Hawking's body began to show signs of amyotrophic lateral sclerosis, or otherwise known as ALS. The disease would, over time, rob him of his mobility and speech. Known cases of ALS would eventually prove fatal, as there is no cure, and this caused Hawking to spiral into depression. His supervisor, Dennis Sciama, would encourage him to continue on with his work. At the time, much was happening in the world of physics, as there was debate in the community over the origin of the universe and its evolution. Hawking believed in the idea of an expanding universe over a static one. The expanding model asserts that the universe must have come from a high density and temperature state. If the known laws of physics are extrapolated to the highest density regime, then the result is a singularity at the earliest moment of creation. Singularities such as these were one of Hawking's main concerns. He tackles singularities by using different types of universes in his thesis. These theoretical universes originated from the Friedmann Equations, first derived by Alexander Friedmann in 1922 from Einstein's field equations of gravitation. Now, by modifying certain density parameters omega, it is possible to create theoretical universes of different properties. For example, by modifying omega naught, it is possible to change the geometry or curvature of the universe, and these were one of the many parameters used by Hawking. In his thesis, these different types of universes were used to show that as long as one were to use general assumptions, then it followed that the existence of singularities in any given universe were inevitable. In 1965, Hawking titled his thesis Properties of Expanding Universes. For this, he was awarded his PhD in Applied Mathematics and Theoretical Physics, specializing in general relativity and cosmology. Very soon after graduation, in collaboration with Roger Penrose, Hawking extended the singularity theorem concepts first explored in his doctoral thesis. Originally, Hawking only talked about the potential existence of singularities within universes, but here he goes on to extend this by suggesting that the entire universe could have started as a singularity. This is very similar to the current version of the Big Bang model physicists use today. Continuing to build his work on singularities, in 1970, Hawking postulated what became known as the second law of black hole dynamics. At the time, there was a glaring problem with black holes. If black holes existed and were indeed singularities, Do they need to obey the laws of physics in the same way as the rest of the universe? Hawking insisted they must. You see, the second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. Hawking's assumption means that black holes, like everything else in the known universe, must also have entropy regardless of its singularity properties. If black holes carried no entropy, it would be possible to violate the second law of thermodynamics by throwing mass of high entropy into the black hole, hence decreasing the overall entropy of the universe. This is not allowed. Hawking postulated that the increase in entropy of the black hole compensates for the decrease in entropy carried by the object that was swallowed. Another troubling feature of black holes was its lifespan and size. If black holes accreted matter, its event horizon would get larger over time. This means that they could only get larger and not smaller, posing a conceptual problem. Hawking solved this by showing that black holes emit very small amounts of thermal radiation at a rate inversely proportional to its size. This happens over time due to quantum effects near the event horizon, causing it to lose mass. Today, we call this type of thermal emission Hawking radiation and is Hawking's most famous equation. Hawking has done a lot of interesting physics up until now, but his public fame did not come until later. Highly skilled in being able to explain complex scientific ideas to the public, Hawking first found commercial success and mainstream fame with his book A Brief History of Time. Here, he attempted to explain how far we had come in our understanding of the universe. As well as this, he was part of a new generation of scientists who believed that science should be for everyone. In spirit of this, he often appeared on different TV shows such as Star Trek and The Big Bang Theory. For the remainder of Hawking's life, he was very fixated on the theory of everything, romanticized by the popular movie also called The Theory of Everything in 2014. The theory of everything is a hypothetical, all-encompassing framework of physics that fully explains and links together all physical aspects of the universe. Needless to say, this was very ambitious even by Hawking standards, and since we aren't masters of the universe yet, he and other physicists have not yet found the solution and probably will not for some time to come. Hawking passed away on the 14th of March 2018 at the age of 76 on the 139th anniversary of Albert Einstein's birth. He was buried in Westminster Abbey, London, alongside the grave of Sir Isaac Newton and Charles Darwin. Inscribed on his memorial stone are the words, "Here lies what was mortal of Stephen Hawking," and his most famed equation, the Hawking radiation, on his epitaph. No doubt, Hawking will be an inspiration for many generations to come. Inclusium et pecula sacra.
If we do discover a complete theory, it should be understandable in broad principle by everyone, not just a few scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of a question of why it is that we and the universe exist. If we find the answer to that, it would be the ultimate triumph of human reason, for then we would know the mind of God.